The world is very focused on energy types today. With global warming, fossil fuel consumption, and the cost of utilities weighing heavily on the minds of many, nuclear energy for many seems to be a light in the darkness. Nuclear fusion creates energy when an atomic atom is created. This type of energy has certain advantages that make it useful, but certain disadvantages that can make it dangerous. In this video, we're going to discuss the problem with nuclear fusion. The video is going to be amazing, so make sure you stick to the end. Before starting the video, be sure to click on the like button and subscribe to never miss out on any of our videos. Fusion uses isotopes in plasma, a kind of flowing gas that responds to electric fields like the gas in fluorescent lights. A fusion reactor heats that gas to extremely high temperatures and compresses it with magnets. But some of the material leaks out and slams into the tungsten armor tiles that line the walls inside of the donut-shaped reactor. A fusion reactor produces neutrons, which can penetrate deep into the walls and create a pathway for the deuterium and tritium to follow. That's an inefficiency in the process and a possible safety issue. When a deuterium and tritium fuse together, their components are recombined to form a helium atom and a fast neutron. As the two heavy isotopes are recombined into a helium atom and a neutron, the leftover extra mass is transformed into kinetic energy. The participating nuclei should be brought together for the nuclear fusion reaction to occur. They should be brought so close to each other that the nuclear forces become active and glue the nuclei together. Every star in the universe, including the Sun, is alive due to nuclear fusion. It is through this process that they produce an enormous amount of heat and energy. The pressure at the core of any star is tremendously high, and that is where the nuclear fusion reaction occurs. On the other hand, the supply of helium, which is required as a cryogenic medium and coolant, may be a problem due to losses during operation and decommissioning. Helium is a rare element obtained as a byproduct in the extraction of natural gas. The danger exists with the natural gas will be used up without the helium being conserved. We estimate the helium demand for a global 30% baseload contribution of fusion to electricity supply and also calculate the amount produced by the power plants themselves. Eager scientists have pursued the harnessing of nuclear fusion's power generating capacity for almost 3/4 of a century. The UK Atomic Energy Authority patented a fusion reactor in 1946. But without reliable success. There are several theoretical methods to attain fusion, but the most exciting in the modern scientific community is thermonuclear fusion. Overcoming that innate repulsion happens in the sun's core because it is under the immense pressure of gravity as well as heat, around 15 million degrees Celsius and 265 billion bar of pressure. On Earth, atmospheric pressure is roughly 1 bar, and the interior of a fusion reactor will need to reach 150 million degrees Celsius, 10 times hotter than the sun's core. Whenever there's a breakthrough in new technology, protection from negative uses is needed. Already with the invention of hydrogen bombs, the chances of their use during war times is a significant threat to humankind. Moreover, with complicated political terms between nations, everyone is looking for alternatives to increase power and dominance by generating more powerful weapons. Although the operational cost is relatively low, the equipment, infrastructure, and conditions required for the reaction to be carried out safely need billions of dollars to start with. Cost and space requirements are also significant limitations of nuclear fusion reactions, as the setup must be hundreds of miles away from the population. Still, researchers are working in a direction to have possible solutions in the future. Magnetic confinement fusion, or MCF, reactors are the most advanced of the two approaches. Unlike magnetic confinement approaches, inertial confinement fusion, or ICF, approaches attempt to externally heat and compress fusion fuel targets to achieve the very high temperatures and even higher densities required to initiate nuclear fusion. Recently, a third approach, which exploits the parameter space between the conditions produced and needed for magnetic and inertial confinement, has gained traction in recent years and is receiving much scientific and even commercial attention. This is called magnetized target fusion, or MTF, sometimes known as magnetized inertial fusion, or MIF. It looks to exploit the use of higher density plasmas for MCF approaches, but lower power lasers and other drivers than those used in ICF approaches. MTF offers a unique route to fusion, and the accelerated development of several unique concepts has seen significant support. In 2020, Canadian nuclear laboratories delivered 5 steel drums lined with cork to absorb shock to the Joint European Torus, or JET, a large fusion reactor in the United Kingdom. Inside each drum was a steel cylinder the size of a Coke can, holding a wisp of hydrogen gas, just 10 grams of it, or the weight of a couple of sheets of paper. This wasn't ordinary hydrogen, but it's rare radioactive isotope tritium, in which 2 neutrons and a proton cling together in the nucleus. At $30,000 per gram, it's almost as precious as a diamond, but for fusion researchers, the price is worth paying. When tritium is combined at high temperatures with its sibling deuterium, the 2 gases can burn like the sun. The reaction could provide abundant clean energy just as soon as fusion scientists figure out how to efficiently spark it. In 1999, Paul Rutherford, a researcher at Princeton's Plasma Physics Laboratory, published a paper predicting this problem and describing the tritium window, a sweet spot where tritium supplies would peak before declining as heavy water-moderated reactors were switched off. If ITER had been doing deuterium-tritium plasma as we planned about 3 years ago, everything kind of would have worked out fine, says Scott Wilms, fuel cycle division leader at ITER. We're hitting the peak of this tritium window roughly now. Scientists have known about this potential stumbling block for decades, and they developed a neat way around it, a plan to use nuclear fusion reactors to breed tritium so that they end up replenishing their own fuel at the same time as they burn it. Breeder technology aims to work by surrounding the fusion reactor with a blanket of lithium-6. Nuclear power plants emit only negligible volumes of carbon dioxide into the atmosphere, and their nuclear fuel chain reaction does return radioactive wastes. The radioactive waste made with fusion is not the same as the fission reaction, and we should not be confused. In a nuclear fission reactor, the radiation is beta particles, alpha particles, and gamma rays, which can penetrate our body, give you all kinds of cancer, and destroy the bonds in your DNA structure. On the other hand, in a nuclear fusion reactor, the vessel wall is the only part that the high-energy neutrons will bombard. In the worst position, if all the enclosing of the main fusion vessel protective layers breaks, the neutron radiation will end as soon as the fusion reaction stops. In a fission reactor, radiation still exists in the waste materials, which means that extreme steps are needed to bury the waste to keep it as far away as possible from people. For nuclear fusion, the activated materials, for example vessels that neutrons have bombarded, should be stored safely for centuries. Also, the radiation level is so small that it can be reused in fusion reactors again. Let us know your opinion in the comments section below. This was all for today. Hope you liked the video. Do not forget to subscribe to our YouTube channel. Stay safe, and we will be back soon with another video.